On February 6, 1951, a Royal Australian Air Force recovery team winched the Wirraway's vertical tail assembly from the mud of Lake Corangamite. They identified it as serial A20-714. They hauled the tail assembly back to shore for transport. The forward fuselage and wings were left behind in the lake. For decades, the official paperwork was filed away, but the fuselage remained effectively missing in action, swallowed by hypersaline brine and the mud beneath it. The recovery operation described in this file is not a search for a lost plane. It is a correction of a procedural abandonment that began during the Korean War. The aircraft was a Commonwealth Aircraft Corporation Wirraway, the backbone of Australian advanced pilot training. This specific machine, a 20714, was not lost to enemy fire or mechanical failure. It was lost to a momentary ergonomic conflict inside the cockpit. On October 23, 1950, trainee pilot Vance Drummond was flying a low-level navigation exercise at around 200 feet. He needed to verify his heading. The magnetic compass in the Wirraway is mounted low, requiring the pilot to look down and reach forward. In the confined geometry of the cockpit, this action carries a specific risk. As Drummond reached for the instrument, his arm inadvertently contacted the control column. This is a control force error. It is a physical interaction with the flight controls that is not an intentional piloting input. The mechanics of a control force error are dictated by the lever arm of the control column. A small displacement at the top of the stick translates to a significant deflection of the elevator. At training speed, the aerodynamic load on the tail surfaces responds instantly to this deflection. The aircraft rotates around its lateral axis. At around 200 feet, the time to impact is measured in seconds. There is no altitude buffer to arrest the descent rate. The pilot's perception lags behind the airframe's response. By the time Drummond realized his hand had pushed the stick, the propeller was already striking the surface. The Wirraway hit the lake like a hard surface. Witnesses described a sheet of water leaping 40 feet into the air. The Wirraway did not disintegrate. It settled into the soft silt of the lake bed. Drummond survived the deceleration. He struggled for roughly 2 minutes underwater to escape the cockpit and reached the surface shaken but alive. With the tailplane still above the water, he clung to it for about 2 hours until a boat reached him. He would go on to fly Meteors in Korea and forward air control in Vietnam. But the airframe did not stay on the surface. It settled into the silt and disappeared. The RAAF returned 4 months later and took what the lake still offered: the vertical tail assembly, the only major piece likely still standing above the waterline. Everything forward of it, the engine, cockpit, and wing center section, was left where it had settled, already sliding into the mud. The evident signature of this site is the separation of the airframe. Most crash sites are concentrated debris fields. This site is defined by what is absent. The empennage is documented as recovered. Therefore, any sonar return or magnetometer hit must correspond to the forward fuselage and the wing center section. This simplifies identification but complicates the survey. We are looking for a blunt, heavy object, not a scattered trail of aluminum. The objective now is to close the file that was left open in 1951. The impact point is known. The question is what remains of a steel tube airframe after 7 decades in hypersaline water. The primary constraint is not finding the wreck, but understanding why it was left behind. The lake is shallow, but the mud is deep. The water is not fresh, it is hypersaline. The environment acts as a chemical clock, slowly dissolving the chromoly steel truss that holds the aircraft together. The lake holds the aircraft in a state of suspended animation. But the environment is not static. Water levels fluctuate. Salinity concentrates. The decision to recover this airframe is a race against the chemical degradation of the steel tube structure. The tail is safe or was scrapped long ago. The engine and the cockpit are still waiting in the dark. When an aircraft strikes a body of water at high speed, the fluid dynamics do not behave like a gentle liquid. Water's inertia and impact pressure turn the surface into something that feels like concrete. The impact is a collision, not a splash. In the case of Wirraway A20-714, the shallow angle of the descent mitigated the total destruction of the airframe, but the energy transfer was violent. That 40-foot sheet of water is the clue. The kinetic energy was dumped almost instantly, arresting the forward motion within a fraction of a second. The fuselage did not skip. It stopped, then it sank. At the crash site, the water was roughly 8 feet deep. The aircraft settled upright, then slowly sank and was increasingly buried as silt shifted and lake levels rose and fell. In a deep ocean crash, the primary environmental enemy is pressure. In Lake Corangamite, it is chemistry, an endorheic basin with no outflow. Water leaves only through evaporation, concentrating the minerals and salts that wash in from the surrounding volcanic plains. The result is a hypersaline solution whose salinity can swing widely, from near seawater to well over double it, depending on drought, inflow, and evaporation. This creates an aggressive electrolytic environment. For an airframe constructed of steel tube and aluminum skin, this is a corrosion accelerator. The upper surfaces of the Wirraway were exposed to this oxygenated brine. The aluminum skin on the wings and the fabric on the fuselage began to degrade almost immediately. However, the weight of the engine and the steel truss pulled the aircraft down into the lake bed. The bottom of Lake Corangamite is not sand. It is a deep, silty mud that can bury a wreck by several feet. In places, close to 1.5 meters, depending on season, wind-driven drift, and water level. This mud created a paradox. While the salt water attacked the exposed sections, the silt enveloped the lower fuselage and the wing center section. The mud acts as an anaerobic seal. It blocks oxygen from reaching the metal. This preservation mechanism is the only reason the recovery is viable today. The steel tube structure inside the mud remains protected from the oxidation cycle that consumed the upper cockpit rails. But this protection comes with a physical cost that complicates the extraction. The mud does not just hold the aircraft, it locks it in place through a phenomenon known as matrix suction. Matrix suction is the resistance created when an object is embedded in a cohesive sediment. Over 70 years, the silt particles have settled tightly around the aluminum skin, displacing the water layer between the fuselage and the lake bed. When a vertical lifting force is applied to the aircraft, water cannot flow underneath to fill the void. This creates a pressure differential. In slow-draining cohesive silt, water cannot rush in fast enough to fill the void, and a temporary underpressure develops beneath the airframe, a breakout suction that can dwarf the lift you expected. The recovery team is not just lifting the Wirraway's empty weight, roughly 4,000 pounds, and certainly not its maximum loaded weight. They are fighting the suction of the lake bed itself. To break this bond, the lift cannot be a sudden jerk. A rapid application of force will snap the corroded longerons before the mud releases its grip. The matrix suction requires a sustained static tension, allowing water to slowly seep into the boundary layer and equalize the pressure. The mud saved the aircraft from dissolving into the salt solution, but now it holds the airframe hostage. The recovery plan must defeat the physics of the suction without destroying the fragile structure that the mud preserved. The most effective survey tool for a shallow, turbid lake is not a magnetometer or a side-scan sonar. It is time. Here, the water level is dictated by rainfall versus evaporation. For decades, the water column hides the wreckage. Then, the cycle shifts. In 2005, a severe drought lowered the lake level significantly. This event opened a specific operational opportunity known as a drought window. A drought window is not merely a period of low water. It is a predictable phase in the hydrological cycle where the submerged terrain becomes an exposed surface, or the water column becomes shallow enough to allow visual penetration from the air. During this window, the water receded enough that the outline of the Wirraway became visible. A local pilot, Gordon Wilson, identified the anomaly. The wreckage was no longer a rumor. It was a verified target sitting in the mud. However, the drought window offers visibility, but it does not guarantee access. In 2005, the water was low enough to see the plane, but the mud was still too deep to walk on. The visual confirmation provided the coordinates, but the environment provided the denial of access. Identifying the target was the first step. Securing the legal authority to touch it was the second. The aircraft is not considered abandoned property. Under Victoria's heritage protections, it is treated as a protected archaeological and maritime heritage site. Disturbing the sediment around the fuselage without the appropriate permit carries heavy penalties. The administrative process to clear the recovery took 12 years. This duration was not due to indifference. It was a negotiation between the requirements of historical preservation, the rights of the local Aboriginal custodians, and the environmental protection of the lake ecosystem. During the 12-year permitting phase, the aircraft remained in the salt. Every year of delay allowed the chloride ions to penetrate deeper into the steel tube structure. The preservation provided by the matrix suction is finite. Eventually, the corrosion front advances past the protection of the silt. The administrative clock was ticking against the chemical clock. By the time the permits were signed, the drought window had closed. The water returned. The target was once again submerged. This created a new geometric problem. The wreckage lies 800 meters from the shoreline. This distance is the primary logistical barrier. At 800 meters, a shore-based crane is useless. The reach is impossible. The water depth is too shallow for a commercial tug or a heavy lift barge. The draft of a standard recovery vessel would ground the hull long before it reached the site. Furthermore, the lake bed is not solid. It is a suspension of deep silt. A truck or a tracked vehicle attempting to drive out to the site during a low water phase would sink to its axles. The team faced a paradox. The water was too shallow to float a crane, but the mud was too soft to support a vehicle. The recovery required a platform that could traverse 800 meters of shallow water, carry the weight of a 2-ton aircraft, and provide a stable lifting point. The solution required a departure from standard salvage architecture. It required a system that could be transported by hand and assembled on the water. This is the concept of modular buoyancy. The team could not bring a ship to the plane. They had to build the ship on top of the plane. A standard commercial salvage barge requires a minimum water depth of 5 to 6 feet to operate its tugs and crane systems safely. Lake Corangamite, in its variable cycles, often offers less than half that clearance during a drought window. If a heavy vessel grounds on the lake bed, it does not sit on firm sand. It sinks into the silt, becoming a casualty itself. The recovery of Wirraway A20-714 required a vessel that could float in inches of water while supporting the dead weight of a fuselage filled with mud. To solve this geometry problem, the team led by Rodney Knights rejected the idea of a single heavy hull and committed to modular buoyancy as a build-on-site solution. Instead of arriving as one vessel, the platform came in pieces, multiple independent flotation units small enough for a light truck or for towing behind a shallow draft skiff. On the water, those units were pinned and braced into a rigid working deck, built where it was needed, directly over the target. The advantage of this system is the draft. By spreading the load of the lifting frame and the crew across a wide surface area of small pontoons, the barge sits on top of the water rather than in it. This allows the rig to make the long, shallow water transit from the shore without plowing into the sediment. The specific configuration for this lift involved assembling a gantry frame directly over the submerged target. This frame acts as a straddle carrier. It provides a stable overhead point for the chain blocks, isolating the lifting force from the instability of the muddy bottom. Beneath the surface, the environment presents a different density challenge. The mud depth is recorded at 2 to 3 feet. This silt is not merely a floor, it is a viscous fluid that envelops the lower fuselage. The aircraft is not resting on the bottom, it is suspended within it. The modular barge must remain stable while the lifting gear engages the airframe. Any sudden shift in buoyancy during the lift could destabilize the platform or shock load the corroded steel truss of the aircraft. The rigging plan focuses on the wing center section. This is the structural core of the Wirraway. It is the strongest point of the airframe, designed to take the loads of flight and landing. However, 70 years of corrosion have altered the material properties. The steel tubes are thinner, the aluminum skin is brittle. The matrix suction of the mud applies a downward force that opposes the lift. If the rigging concentrates the tension on a single point, the structure will fail before the mud releases. The team positions the barge. They lower the slings into the dark, saline water. They must feel for the spar under the mud, guiding the straps by touch. There is no visibility. Every connection is verified by hand. The platform is stable. The gantry is locked. The chain blocks are taut. The recovery is now a static battle between the buoyancy of the barge and the adhesion of the lake bed. The aircraft is ready to move, but the mud has not yet conceded its grip. A vertical pull on a mudlocked airframe is a recipe for structural failure. The suction does not yield instantly. If the lifting force exceeds the tensile strength of the corroded steel longerons before the sediment releases its grip, the fuselage will snap in half. The recovery of Wirraway A20-714 in late August and early September 2021 relied on a specific tactical decision. The team could not simply winch the aircraft out of the lake bed, they had to peel it loose. The process begins with the application of static tension. The chain blocks on the modular buoyancy rig are tightened until the straps take the weight. The gantry takes the load, compressing the pontoon slightly into the water. At this stage, the aircraft does not move. The objective is to create a constant upward vector that encourages water to seep into the boundary layer between the aluminum skin and the silt. Matrix suction, exploited in reverse. By maintaining tension, the team waits for the pressure differential to equalize. As the water slowly penetrates the mud seal, the cohesive friction drops. The bond breaks not with a snap, but with a slow, viscous release. The mud yields. The fuselage, heavy with 71 years of accumulated sediment, begins to rise through the water column. This is the critical phase for the airframe. As it lifts off the bottom, the support of the silt is removed. The steel tube structure must now support its own weight, plus the weight of the mud packed inside the wings and the engine cowling. The lift speed is kept dead slow. The Wirraway is brought to the surface inch by inch. The first component to break the waterline is the rollover truss behind the cockpit, followed by the engine firewall. The structure is coated in a thick layer of gray silt, but it is intact. The decision to use the wing center section as the primary lifting point proves correct. The load path transfers through the spars, bypassing the fragile tail section that was already compromised or missing. As the aircraft clears the water, the full extent of the preservation becomes visible. The mud has done its work. The lower sections of the fuselage, those that were buried deepest, show remarkably little corrosion compared to the upper rails, which were exposed to the oxygenated brine. The fabric skin is gone, dissolved decades ago, but the metal skeleton remains. The Pratt & Whitney engine, a complex assembly of steel and alloy, hangs heavy on the mounts, still bolted to the frame. The recovery team secures the fuselage to the barge. They have successfully extracted the main body of A20-714 from the environment that claimed it, while other major sections may require separate lifts. The operation has converted a submerged anomaly into a recovered artifact. The risk of structural collapse during the lift has been managed. The physics of the Mudlock have been defeated. However, as the water drains from the fuselage, the chemical equilibrium shifts again. The aircraft is no longer protected by the anaerobic silt. It is now exposed to the atmosphere. The oxygen in the air begins to react immediately with the chlorides trapped in the metal pores. The corrosion process, which was slowed by the mud, will now accelerate exponentially if the surface is allowed to dry. The successful lift is not the end of the danger. It is the start of a new, faster race against entropy. The aircraft is out of the lake, but it is effectively burning in slow motion. The team must transition instantly from recovery to stabilization. Once the fuselage is in air, trapped chlorides and fresh oxygen turn damp metal into an active corrosion cell. Stabilization is no longer optional. It is the only way to keep the structure from accelerating toward failure. The solution is not a simple wash. The salts are not merely on the surface, they are trapped throughout the structure. A standard conservation approach is a long-term desalination bath, submerging the aircraft in fresh water, often with inhibitors, and cycling that water as chlorides diffuse out over time. The tank water has to be tested and changed as the salinity climbs, because this is not a process measured in hours. To reverse 7 decades of absorption, the desalination cycle may take years. That is why the team moved the fuselage from the lake edge straight to a conservation facility and kept it wet in transit, preventing the first wave of salt crystallization. The immediate goal is stabilization. Preserve what was recovered so it can be studied and displayed without crumbling. Any eventual return to flying condition remains a long-range ambition, not a promise, given the corrosion of the primary load-bearing members. The objective is conservation first. Keep the artifact intact. This preservation effort saves the physical evidence of a specific human survival story. When the aircraft hit the water in 1950, trainee pilot Vance Drummond was trapped in a darker, more immediate crisis than corrosion. He was underwater, inverted or sinking, struggling with his harness in a crushed cockpit. His escape was a matter of disciplined procedure under extreme duress. Drummond survived the lake to have a distinguished career. He served in the Korean War, where he was shot down again and survived as a prisoner of war. He later served in Vietnam. The pilot moved on, but his first aircraft remained in the mud, holding the shape of the cockpit exactly as he left it. The recovery of the fuselage in September 2021 finally reunites the airframe with its history. The tail section, recovered by the Royal Australian Air Force in February 1951, is long gone, likely scrapped or lost to time. But the main body of the aircraft, the engine that drove it, and the controls that Drummond held are now secure. The gap in the record is closed. The project demonstrates that even in a harsh hypersaline environment, the combination of anaerobic mud and careful engineering can preserve history. The modular barge defeated the access problem. The slow tension defeated the suction. Now the fresh water bath is defeating the salt. The Wirraway is no longer a missing number on a rusted serial plate. It is a recovered asset, owing its survival to the depth of the silt and the persistence of the team that refused to leave it behind.